You know, every single time you stream a movie, post something on social media, or even just search for something online, you're tapping into a system so huge, so complex, it's basically invisible. These are the engines that power our entire digital world. They're called distributed systems. So today, let's pull back the curtain and really see how these incredible systems came to be and what makes them tick.
To really get where we are now, we have to look at just how far we've come. So picture this. It's 1988. You want to download one song, not an album, just a single song. You would have had to wait over 6 hours for it to finish. 6 hours. Streaming an HD movie, that was pure science fiction. This was the bottleneck, right? This massive wall we had to break through. And it was about to spark a total technological explosion. And that leap from a 6-hour song download to instant 4K streaming, well, it wasn't magic. And it wasn't just one single invention. It was actually the result of 4 huge, powerful technologies, all rocketing forward at the same time, completely changing what was even possible.
First up, networks. Back in the 80s, they were pretty rare. But then Ethernet technology just took off, and the speeds went through the roof. Exponentially. We went from a sluggish 10 megabits per second in '85 to a mind-blowing 100 gigabits by 2009. Data networks went from being this niche thing to being a cheap, scalable, and super fast foundation for everything.
Okay, next revolution, computer memory. And the scale of this price drop is it's staggering. In 1977, get this, a single megabyte of memory cost around $32,000. By 2012, it was less than a penny. This wasn't just about saving a few bucks. This is what unlocked our ability to run really complex stuff, like photo editors and games right inside our web browsers.
And you know what? The exact same thing happened with storage. In 1977, trying to get 1 gigabyte of storage would have cost you over $11,000. And you would have needed more than 2,700 floppy disks to do it. It's wild. By 2012, that same gigabyte cost less than a nickel. This shift is the reason you can carry a massive library of thousands of movies and songs right in your pocket. And the final piece of the puzzle, the processor itself. The whole idea of what a computer even is completely changed. We went from having one gigantic, multi-million-dollar machine that took up an entire room to filling that same room with racks holding tens of thousands of cheap, powerful, and incredibly efficient computers. So, these 4 revolutions gave us lightning-fast networks and computers that were cheap and powerful. But the real magic, the true value, that happens when you start connecting all of them together on a massive, massive scale. And this brings us to a really key idea called Metcalfe's law. Basically, it says that a network's value doesn't just grow one by one as people join. No, it grows exponentially. Every new connection creates a ton of new possible interactions, which makes the whole system way more powerful for everybody. Let's try to put that into perspective. Back in 1985, the entire internet, the whole thing, had fewer than 2,000 connected computers, or hosts. It was just this tiny little academic network. Now, fast forward to 2012. That number had exploded to over 888 million. That right there is Metcalfe's law in action. That incredible, explosive growth in connections is what created the fertile ground for services like eBay, Facebook, and Google to even exist. All of their value comes directly from the massive size of their communities. Okay, so we've got hundreds of millions of cheap, powerful computers. They're all connected by these super fast networks. How on earth do you manage all of that? How do you make it useful? Well, that's where this idea of the invisible computer comes in. This here is the classic definition, and let's break it down, because both parts are absolutely critical. First, it's a collection of independent computers, right? All those separate machines on all those racks. But second, and this is the really cool part, they appear to the users as a single computer. All of that crazy complexity underneath is completely hidden from you. This goal has a name. It's called creating a single system image. The whole point of the software in a distributed system is to take thousands or even millions of separate parts and present them to you, the user, as one single coherent thing. Think about it. When you use a search engine, you don't see the thousands of servers scrambling to answer your question, you just see a search box. That's the single system image at work. Now, as you can probably imagine, building these invisible computers is a monumental engineering challenge. Where do you even start? Well, the architects first have to decide on the fundamental way these thousands of machines are going to process information together. Look, we don't need to get totally lost in the weeds here, but a classification system like this one, Flynn's taxonomy, it helps show the different basic approaches. A traditional computer is SISD, one instruction, one piece of data. Simple. But something like a modern graphics card is SIMD. It runs a single instruction across tons of data all at once. That's a form of parallelism, basically doing many things at the same time. Designing a distributed system means making these kinds of architectural choices, but at a ridiculously massive scale. So we've covered a lot of ground, right? From network speeds all the way to system architecture. But why does any of this technical stuff actually matter to you in your day-to-day life? All right, let's put it all together. Those four big tech revolutions gave us the raw materials, cheap computing power, and super fast connections. As more and more devices got connected, the value of that network just exploded. And to manage this huge, complex web, engineers created distributed systems, these invisible computers that make thousands of machines act like one. And that invisible computer is what powers pretty much every single digital service you use today. You know, we started this journey looking way back at 1988. The source material we're looking at took us to 2012, with almost a billion connected devices. Today, that number is many, many billions more. From our phones to our cars to our refrigerators, and the core ideas of distributed systems are what make this constantly expanding world possible. Which kind of leaves us with one last big thought. What new, incredible, maybe even inconceivable services are going to emerge when the next billion devices come online?